Okay, so we are going to review the homework from chapter 5 to 8 today. And after our review, we are going to have an exam. Not tomorrow. Tomorrow we are going to go over chapter 9, but we are going to have an exam on Thursday. Wednesday is a national holiday, it's the Juneteenth, but I will post the exam Wednesday afternoon. So you have Wednesday afternoon and also the whole Thursday to finish that. And the due date will be Thursday midnight at 11:59 p.m. Okay, so that's our plan. And the Friday we are going to have another lecture which is about chapter 10. So you can see all of our homework here. So we are going to go over the homework. I already give you time to finish to try your homework, and then you can compare your answers with mm, my solution here and what we are going to go over here. Okay. So let's take a look at chapter 5. What is chapter 5? Chapter 5 is about forces. So forces and also Newton's laws of motion. So we are going to go over that. So let's take a look at the first problem. We have three forces. So we have three astronauts propelled by jet backpack. So 1, 2, 3. Push and guide a 120-kilogram asteroid toward a processing dock. Exerting the forces shown in the picture, we have, if it's not very clear to you, we have F1, F2, F3. So F1 and F2 have an angle to the x-axis, which is 30 and 60. So what is the asteroid acceleration? A, in unit vector notation, and B, magnitude, and C, the direction relative to the positive x-axis. So how to do this problem? In order to do this kind of problem, you need to find the xy component of the forces. So what we do is we resolve the vector first. Going to make it a little bit bigger. Okay, so here you have to get your you have to draw F. So let me write it. You have to find out F. Oh, it's good. Okay, it's good. So you have to find out F1x and then F1y and then F2x and F2y, and also you are going to find F3x and also F3y, and after that you are going to add all the x component and add all the y components. Okay, so let's try to do the x component for F1. So F1 here, this is the angle. We should do F1 cosine theta. And that will be, so you can kind of write it, F1 is 32 Newton. You can go back to the problem. F1 is 32 Newton. Angle is 30 degrees. So it's 32 multiplied by cosine 30. X component is the cosine, okay? And then you are going to get 27.7 Newton. And then your F1y, you are going to use it is F1 sine theta. And what you are going to get is 32 sine 30. and you are going to get 16 Newton. And then F2x, you can see F2 is along x direction, so this is 55. And then this will be, what's this? 2y along x direction, so it does not have 0 component. So it's 0 Newton. I'm going to change my pen. You do F3, X, and Y first, okay? I'll be right back. I'm going to change my pencil for this laptop. Okay. So F3x, what is F3x? F3x, you should also write F. So it's F3 times cosine theta 3. And you are going to get 41 times cosine. Forty-one times cosine 60, and then you are going to get 20.5 Newton. And also F3, but be very careful. This angle is 60, but F3, you are going to have a negative component, okay? It's going down. F3, the magnitude. See, the F3, the magnitude is actually, you can write like this, is F3 times sine 60. And then you are going to get 35.5 Newton. But F3, if this is F3, F3 goes down. So when you F3y goes down. So when you add them, you have to have a negative sign here. So I'm going to write it like this. You can kind of write a negative sign here. So you do the summation, you know this is negative. So the net force will be equal to, for x direction, you are going to add this to this to this. So it's 27.7 plus 55 and then plus 20.5. And you are going to get, add this 3. So you are going to get, this is 47, 40, 48.2. You are going to get 113.2 Newton. Okay, and also you can get your net force along y direction, which is 16 plus 0, and then minus 35.5. Okay, so we can get our net force along y direction, which is 16 minus 35.5, and you are going to get 16 minus what you are going to get. You are going to get negative 19.5 Newton. Okay, and after that, you have to calculate your acceleration. Your acceleration will be equal to net force divided by the force divided by mass. Okay, net force along x direction, and AY will be equal to net force along y direction divided by m. And after that, you are going to get acceleration along x direction, which is 0.86 meters per second square. And AY, you are going to get negative 0.16 meters per second square. Okay. So after that, you are going to calculate. So you are going to write it this way. Your acceleration will be equal to 0.86 I minus 0.16 J. Okay, so very simple. And this is the unit vector form. So what is this? This is the unit vector notation. And after that, you also have to go back. After that, you also have to calculate your magnitude. So magnitude, you are going to write it this way, is 0.86 square, and then plus 0.16 square. That's your magnitude, and then take square root, okay? So this is your x component, and this is your y component, and you are going to add negative 0.16 square, and you are going to get 0.875 meter per second square. That's your acceleration, and then the magnitude. You got it? The angle. The angle, actually we can kind of like draw it. So this will be our acceleration, look like this. This is 0.86, and then this is 0.16. So your angle, I'm going to write it here. Angle will be inverse tangent y over x, okay? So it's 0.16 over 0.86. Thick. Okay, and then you are going to get 10.5 degree. So here, this angle is 10.5 degree, and it's below. So it's below the positive x-axis. Okay, so this is how you do it. When you see problem like this, the forces are given to you, you are going to resolve the vector and then try to get all the force along x direction, try to get all the force along y direction, and then put the net force together. So you will be able to get your net force, and you will be able to get your acceleration. Problem 19 is very simple, okay? So you have to get your acceleration first, and then use acceleration times the mass to get the magnitude of the force. So in order to do that, you have to get V equals to 1600 kilometer per hour. So it's a 500 kilogram rocket sled can be accelerated at a constant rate from rest to 1600 kilometers per hour in 1.8 seconds. So this is in second, this is in kilometer per hour. You have to convert this. So it's 1600 times 1,000. You are going to get this in meters and divided by 3,600 seconds in an hour. So after that, you are going to get 444.4 meters per second. And also, you can get your acceleration using V final will be equal to V initial plus AT. Okay, so from rest is 0 plus A times T is 1.8 second will be equal to 444.4 equals to that. And after that, you can get your acceleration. Your acceleration will be equal to this divided by 1.8. So I'm going to get 247 meters per second square. And then after that, you can get your force equals to mass times acceleration. and it's 500 times 247, and you are going to get 1.235 times 10 to the power 5 Newton. Okay, so this is our force and acceleration. And then problem 57 is very complicated. You have a pulley here with connect these two masses, and you are going to calculate the acceleration, the forces, and also the tension along the cord. So we take a look at this problem. We have block M1 3.7 kilogram here on a frictionless plane, inclined at angle equals to 30 degree, and is connected by a cord over a massless frictionless pulley. And remember, this is a frictionless surface, so when you do free body diagram, you do not have friction, okay? So the other mass is 2.3 kilogram. So what are A, the magnitude of the acceleration for each block, and B, the direction of the acceleration of the hanging block? So this guy here, M2. So you are going to find A1 and A2 and the direction of A2. And then C, the tension in the core. So you are going to calculate that. What we are going to do, we are going to do free body diagram first, okay? So take a look at M1. I can do it on the picture here. So this is M1. We are going to have gravitational force, Fg1. We are going to have normal force, Fn. Or we can use N. I usually use Fn, okay? And also the tension here, okay? The tension should be this way because it's pointing from the object to the cord. And this guy here for M2 also have tension this way, and you have Fg2, okay? So after this, this is free body diagram. We have to define the direction of motion. So let's just using the conventional setup. We are going to define going up. So for M2, I'm going to write here. So for M2, we are going to define going up is the positive y direction, and this is x direction. But for M1, usually our direction of motion is the positive x direction. So for M2, it's easier for us to define our xy like this, okay? X and y. So we can do Newton's second law for M2. So for M2, what we have? We are going to have net force along y direction. They have acceleration, okay? So we assume the acceleration it's going, let's assume acceleration goes up. Okay, so we can assume acceleration goes, let's assume acceleration goes down. Okay, so that it was going this. Doesn't matter. So we assume our acceleration for M2 is going down, and our acceleration for M1 is going to the right. So we are going to have this. Okay. So after that, let's do net force along y direction will be equal to tension going up minus Fg2. If our acceleration goes down, should it be negative M2A. Okay, be very careful if we think acceleration goes down. But if we get a positive value, if we get a negative value, that means our assumption is not right. Okay, so we assume M2 goes down. Okay, assume, and then goes down, then we are going to have this negative sign means goes down. If you get a negative value, that means our assumption is not right. So we assume that. And then for M1, what do you have? M2 x direction, no motion, so we don't have to worry about the x. And for M1, we have here is we should have our net force along x direction. We have two forces. It's T. So this tension is along x direction and tension is positive. And we also have the x component for our Fg. but it's negative. So minus FG1 times. So here, this angle is also theta, and this is your x component of F1G. If you take a look at this, but you shouldn't draw this in your free body diagram, okay? But this is our x component of our gravitational force, and you should do sine theta equals to, so here we assume our acceleration go this direction, so it equals to m1a. Okay, and then our net force along y direction, we should have our normal force minus Fg1 cosine theta equals to 0, okay, because no motion along y direction. So this is our Newton's second law. And then what else we need? We need take a look at everything here. What are the things that we need to calculate? See, we have to calculate our acceleration and we have to calculate our tension. Okay. The problem didn't ask you to, actually it asked you to calculate tension. So we need acceleration and tension. And take a look at the equation here and here. We have F1 and F2, Fg2 and Fg1 that is given to you. The mass 1 and the mass 2 are given to you. So the only thing we need is put these two equations. I'm going to write here. So we are going to use these two equations, put these two equations together and get our number in, okay? So what do we have? I'm going to write this is 1, this is 2. So equation 1, we are going to get tension minus M2G will be equal to negative M2A. And then for second equation is tension minus M1G sine theta. Sine theta is sine 30 degree will be equal to M1A. Okay, so M1 and M2 are given to you. You can just replace. So this is two equation with two variable. So we can have our, so from here, we will get our tension equals to M2G minus M2A. And then you can put your tension in here. You will be able to calculate your acceleration. I'm going to write it here. So basically, replace the tension in the second equation. You are going to get M2G minus M2A minus M1G sine 30 will be equal to M1A. And then you can get your A. So your A will be, I'm going to get a symbolic solution first, okay? So you can plus M2A on both sides, and you are going to get M2G minus M1G sine 30. Okay? And then divided by M1 plus M2. And then you are going to get, put your M1, M2 in, so 2.3 times 9.8, then minus 3.7 times 9.8 sine 30 over 6. 2.3 plus 3.7 over 6. And then you are going to get your acceleration is 0.735 meters per second square. And then you are going to get your tension will be equal to, see here, what our tension is. Tension is M2G minus M2A. And you are going to get your tension equals to 2.3 times 9.8 minus acceleration 0.735. Then you are going to get 20.8 Newton. So your acceleration is positive. That means our assumption is right. Our acceleration should go down, okay? So acceleration go down. A goes down. And then our tension is this. Okay, so this is chapter 5 problem. And then we are going to do chapter 6. So figure 620 shows an initially stationary block of mass m on a floor. A force of magnitude 0.5 mg is then applied at an upward angle theta 20 degrees. So 20 degrees here. So what is the magnitude of the acceleration of the block across the floor if the frictional coefficient is 0.6 for mu s and 0.5 for mu k and 0.4 for mu s and 0.3 for mu k. So what does this mean? You are going to find out the force applied on x direction, okay? So for this one here, let's do a free body diagram. You have frictional force, you will have your normal force. When you do free body diagram, think about the forces. You have gravitational force and you have, your F is not horizontal. You will have this F here, 20 degree, okay? So, and this is 1/2 mg because it's 0.5 mg, okay? So after that, what you do, you are going to, so once you get this, you already have the xy coordinate, so you are going to get your net force along x direction and then net force along y direction. So x direction, we should have F times sine, it's not sine, it's actually cosine. Cosine theta minus f. Okay, we do not know if it's moving or not, so let's just write it this way, equals to ma. Okay, depend on your magnitude of your frictional force, we will see how it works with your how f cosine theta compared to your f, see if we can get an acceleration. And then for y direction, we have normal force plus f times sine 20, and then minus fg equals to 0, because y direction, we do not have acceleration. So from here, you are going to get your normal force. Your normal force will be equal to mg minus F, this is 1/2 mg, okay? So 1/2 mg sine 20, and you are going to get, you can do the calculation. Here we have half sine 20 is like 0.342, and then you are going to get mg times 1 minus 0.5 times 0.342. This is sine 20, okay? And then multiply by, and then you are going to get 0.83 mg, okay? So very good. And after that, what's the next step? You are going to get your maximal, Fs maximal, using your normal force. So say here, Fx frictional force maximal should be normal force times mu s. So you are going to get 0.6 times 0.83 mg, and you are going to get 0.498 mg. Okay, so 0.498 mg. And here, your F cosine theta, you can keep on writing here. F cosine theta is F cosine 20 minus F, and F cosine theta, this is 0.5 mg, okay? So 0.5 times cosine 20, you are going to get 0.47 mg and minus F. And you can see this 0.47 is smaller. So here, your Fx, which equals to F cosine 20, that is 0.47 mg, is less than Fs maximal. So the block will not move, right? because it didn't overcome the maximal static friction, and your acceleration will be 0. Okay, so your acceleration is 0 for part A. But for part B is a little bit different. Part B, we are going to have our static friction, which is 0.4. So you are going to write here, if our Fs maximal for part B will be equal to Fn times mu s, and that is 0.4 times 0.83 mg. And then you are going to get 0.332 mg. And it's less than our Fx because our Fx is 0.47 mg. So that's why the block will move, right? The block will move. Once we know it moves, we can calculate the acceleration. Its net force along x direction will be equal to F cosine theta minus kinetic friction equals to ma. So that's why we can do 0.47 mg minus, what is the coefficient? Minus Fn times mu k equals to ma. Okay. So here, this is 0.47 mg minus 0.83 times 0.3. Because our mu k, it will move this kinetic friction, and then our mu k is 0.3. We should put a 0.3 here, and then it equals to ma. Okay. And this is mg, do not forget 0.83 mg. And the mass get crossed out for each term. So our acceleration will be equal to, do the calculation, you are going to get 0.221 g multiplied by g, and then that's 2.17 meters per second square. So for part B, it will move, and this is our acceleration. Okay, for point 1, for part A, it will not move. Okay, so this you are going to have something like this on exam. I will ask you if the block will move or not, and if it moves, what is the acceleration? Yeah, like that. Okay, so this is that problem, and then we are going to take a look at problem 16. So 16 is a loaded penguin sled weighing 80 Newton rests on an incline at an angle 20 degrees to the horizontal. So between the sled and the plane, the coefficient of static friction is 0.25 and the coefficient of kinetic friction is 0.15. So what is the least magnitude of F1 parallel to the plane that prevents the sled from slipping down the plane? So you are going to find, do a free body, find the F here. And then B, what is the minimal magnitude of F that will start the sled moving up the plane? And what is the value of F is required to move the sled up at a constant velocity? So this is 3 problem, but we are going to just have one free body diagram. What do we have? Oh, actually, for A and B, the free body diagram is a little bit different because the direction of our friction. Okay. But the always we have is gravitational force, we have our normal force, and then we have our friction. For friction for part A is this, okay? Because it tries to slide. So because here we try to put a minimal force to prevent this sled from slipping down the plane. Okay? So we are going to have from slipping down. Actually, from slipping down. So it slipping down is this direction. So our F static friction should be going up. This is part A. Let me do the free body diagram one by one because For B, when it is moving up, then your friction will be go down. Okay, so let's do this. So for A, we are going to have the flat. We are going to have our F this way. We are going to have our FG this way. We are going to have our normal force this way. The sled will sliding down. So we are going to have our maximal static friction here. Okay, so what do we have? It's along x direction, we should have F plus the maximal static friction, and then minus Fgx goes to 0. Okay, you know why? We can set this is our positive x direction, this is our positive y direction, no motion yet, so it equals to 0. F plus Fs minus Fgx equals to 0. And then our Fy direction, we should have our normal force minus Fg. This equation, y direction, is always right for all the three situations. So Fy will be equal to Fn minus Fg times cosine theta equals to 0. So you are going to get your normal force equals to Fg cosine 20, and then it will be equal to 80 times cosine 20. Okay, so 80 times cosine 20, which is 75.2 Newton. So this is Fn is a constant in three situations. So I'm going to write the Fn equals to 35.2 Newton here, and this is 80 Newton here. Okay. So the y direction we don't have to worry about because y direction is always the normal force. And then if you want to get your Fg, if you want to get your F, then our Fs maximal, this is static friction, will be equal to mu s times Fn. So mu s is 0.25 and multiplied by 75.2 Newton. Okay, so you can get your maximal static friction will be equal to 18.8 Newton. And then you put it back. It's F plus 18.8 Newton, then minus Fg, which is 18 times sine 20 equals to 0. So your normal force, so your applied force, this is not normal force, your applied force will be equal to Fg 80 times sine 20 minus 18.8 Newton. And then what you got, you are going to get 8.6 Newton. Okay, so this is our calculation. And this is the first part, and part B. Part B will be very similar, but part B, what you have is you have the sled moving up. So if you have your sled moving up, you are going to have the same thing. You are going to overcome the maximal static friction, and then this is your normal force, and this is your gravitational force. So here, your Fx will be equal to F minus Fg, and the minus Fs maximal, which equals to 0. So your F will be equal to Fg plus Fs maximal, okay? Because we are going to move up. So your static friction. So this is the relative motion, and your static friction should be the opposite direction. So that's why you should have 80 gx, don't forget. 80 times sine 20, and then plus 18 point, we get this here, 18.8 Newton. And then you are going to get 46.2 Newton. Okay, so this is for part B. And then part C, it's what value of F is required to move the sled up at constant velocity. So if it's moving, let's see, moving, then Fk exists instead of Fs. So on the x direction, you are going to have your F. I'm going to do it again. This is Fk, and this is your Fg, and then this is your normal force. Okay. And then what we have is our net force along x direction will be equal to F minus Fgx, and then minus Fk, okay, equals to 0. So F minus 80 times sine 20. And instead of using 0.25, we have 0.15, that is our friction. So our normal force is 75.2, and then we should use 0.15 times 75.2 equals to 0. This is your mu k, and this is your Fn, okay? And then your force, do the calculation, your force will be equal to, do the calculation, it's 80 sine 20 plus 0.15 times 75.2, and we are going to get 38.6 Newton. Okay, so this is that. It's a little bit complicated, okay? So now we take a look at problem 52. 52 here, we have to get our centripetal force, and also what is the centripetal force. So an amusement park consists of a car moving in a vertical circle on the end of a rigid boom of negligible mass. The combined weight of the car and the ride is 5,000 Newton. The circle is a radius of 10 meters. So this is 10 meters. At the top of the circle, what are FB and the direction of the force on the car from the boom if the car's speed is 5 meters per second. So what is FB? FB is this little boom acting on the car. So we can assume that our FB goes down, okay? So it's pushing the car down. But if we get a negative value, then it should be go up. So here for this car, what we have? We will have FB going down, and we also have our gravitational force going down. And what we should have is, this is all the forces acting on the car, and it should be equal to your centripetal force, because this car is doing circular motion, which equals to FB plus FG, which equals to M times V squared over R, okay? And also be very careful, what is your mass? mg will be, Fg will be equal to mg, which is 5,000 Newton. So your mass is 510, okay? 5,000 divided by 9.8, which you are going to get 510 Newton. So here what we have is our FB. So FB plus 5,000 Newton will be equal to mass, which is 5. Oh, sorry, this is the kilogram. Mass is in kilogram. So 510 kilogram multiplied by 5 square divided by 10. Okay, so when you do this calculation, actually you are going to you'll get your FB, which is negative 37 and 24.5 Newton. So our FB goes, so this is negative, it's the opposite direction of our assumption. So FB goes up and the magnitude is and then you are also going to get when the speed is 12. This is very simple. Just repeat your calculation. But this is 12. So I'm going to write here. Everything is the same. You just do FB plus 5,000 will be equal to 510 multiplied by 12 square. So this V instead of 5 is 12 square divided by 10. And then your FB, so put it here, you should get a positive value. So 2,347 Newton. So this is a positive value, so it actually goes down, the same as our assumption. Okay. So this is this calculation. This problem is actually pretty simple. Compared to like this guy and also this guy. But you are going to see problem like this on your exam, okay, not like number 10. Okay, so we are going to take a look at chapter 7. For chapter 7, the first two problems are very simple. I think I can give you the problem. Yeah, the first one is very simple. You are going to calculate the kinetic energy and compare to a TNT. You can read the problem by yourself. The meteorite has this amount of mass and this amount of speed. So we are going to calculate the loss of energy in joules when the meteorite is hit the earth. Okay, so what we do here is because when it hit the earth, it will stop, right? So our final speed will be 0 meters per second, and our initial speed will be 15 kilometers per second, which is 15,000 meters per second. So our changing of kinetic energy is 1/2 m v final square minus 1/2 m v initial square. And our mass, this is a big mass. Okay, mass is 4 times 10 to the power of 6 kilogram. So it's 0 minus 1/2 4 times 10 to the power of 6 and 15,000 square. And you are going to get a very large number. It's negative 4.5. So this is our lost energy. Okay. And here we have TNT, megaton of TNT, it's this amount of joule. So convert this to TNT, it's 4.5 times 10 to the power of 14 divided by 4.2 times 10 to the power of 15 joule. So it's about 0.1 megaton. Megaton of TNT. Okay, so this is that. And then here you are going to atomic bomb was equivalent to this amount of TNT. So this compared to the atomic bomb, oh, this is very so the atomic bomb is 13 kiloton of TNT. Okay, so basically it's 0.1 megaton times 1,000 kiloton per 1 megaton. Okay, 1,000 kiloton is 1 megaton, so it's 1 bomb, and it's 13 kiloton. Okay, so here, so this is for the meteorite. Okay, and it will be equal to 7.7 atomic bomb. Okay, you should get a 7.7 atomic bomb. So when it hits the Earth, it's like you have 7.7 atomic bomb that was throwing, like happened on Earth. So this is that. And the problem number 10, this is a very simple one. You can use, I can give you the answer because we do not have enough time to finish everything for today. Let me show you. Because we have the force, right? Oh, no, we have the force. We have the displacement, which is 3I and 4J, and our force is 2 Newton. So basically, you have to do you have to find the angle. Okay, so I'm going to draw the picture here. One is here. This is our displacement, and our force is here. This is 100, and you are going to calculate this angle so that you can calculate our angle between them. So here, this angle theta, let me do it. This angle theta will be equal to inverse tangent 4/3. And you are going to get 53.1 degree. So our angle phi, I'm going to label this as phi, will be equal to this. Yeah. Choose angle phi. This is angle phi. Phi is 100 minus 53.1. So you are going to get a 46.9 degree. And then your work will be equal to F times D times cosine phi. And then it's 2 multiplied by, this is 3 square plus 4 square, and take square root. So it's 5 cosine 46.9, and you are going to get 6.83 joules. So this is this problem. This is a very simple problem. And also problem 17, it's a very simple problem. You have to calculate so you have to calculate the force. The force you can use use Newton's second law, and then the work will be equal to force times the displacement. Okay, so you are going to calculate the work, and you are going to calculate the kinetic energy and the speed. So I'm going to, so for helicopter, I'm going to write here, the force by the helicopter will be equal to, you have acceleration, will be equal to m. I'm going to write it this way. It will be equal to mg plus ma. So it will be equal to m times 11/10g. Okay, so I'm going to write it this way, 11/10 mg. So this is the helicopter because it has acceleration, so it have gravitational force plus acceleration. You are going to get a helicopter. So you are going to get your work done by the helicopter will be equal to Fh times d. Distance is 15. So it's 11 over 12 times, not 11 over 12, 11 over 10. 11 over 10, 11 over 10 multiplied by m multiplied by g multiplied by 15, and then you are going to get 11,640. But your gravitational force will be equal to negative Fg times d, which is mg, negative mg times 15, and then you are going to get negative 10,580 joule. And also, what you are going to calculate? You are going to calculate the kinetic energy, right? So here, it's change of kinetic energy will be equal to net work done on the object. So you are going to use this value plus this value. So 11,640 and then minus 10,580. And then you are going to get 1,060 joule, and then you are going to calculate the speed. Okay. So you are going to calculate the speed. Speed delta k will be equal to 1/2 mv squared. And then it's 1,060 times 1/2, 72 v squared. And then you are going to get your speed equals to 5.4 meters per second. So this is this problem. I think the only thing that is a little bit difficult is try to get this, the mass or the force by the helicopter. Okay. So now we are going to take a look at 29. 29, you have to find out the joules. Okay. Let me see. Actually, 29 is not on our exam. Let's be we're good. Let's skip 29 because that's the yeah, let's skip 29. 29 is not our exam. I don't have this kind of problem, this figure problem on exam. Yeah, so let's skip 29. You still have to do it. I will post the solution of this on D2L, but let's skip this problem for now because we don't have anything like this on exam. Okay. So let's keep on going to chapter 8. So chapter 8, let's take a look at problem 53. Okay, 53. Here we have a 3-kilogram block is accelerated from rest by, because you have to know how to do conservation of energy and what is the thermal energy, okay? Thermal energy is the work done by the frictional force. So we have this guy accelerated from a compressed spring of spring constant 640 Newton per meter. The block leaves the spring at the spring's relaxed length and then travel over a horizontal floor with a coefficient of kinetic friction mu k is 0.25. The frictional force stops the block in distance, which is 7.8 meters. So this part, you have to use this to calculate your thermal energy. So what are A? Increase in thermal energy of the block floor system and the maximal kinetic energy of the block, and then the original compression distance of the spring. So you are going to see what converted to what. So from here, see this little guy here, going from here to here, it your kinetic energy converted to thermal energy because you have friction here. And how to calculate the thermal energy? So here, for motion with friction, you have to do, E thermal, right? When you have friction, the thermal energy, that is right. And then you have to do frictional force will be equal to mu K times the normal force times the D. And then normal force actually is the gravitational force in this case. So because I'm going to do here, Fg, and then normal force. And here, this way, you are going to have friction. You're going to have friction, Fk. Okay, and then 0. You do not have, one thing I want to remind you, you do not have spring force in this area because it's at relaxed state here, okay? So it's 0.25 times 3.5 times 9.8 times 7.8, and then you are going to get, 66.9 joules. And after that, you are going to calculate the maximal kinetic energy of the block. So it is when it was entering the frictional, it's the moment when he enters the part when we have friction, because after that kinetic energy converted to friction. So our maximal kinetic energy, so K maximal happens just before the block enters the frictional surface. So our K maximal should also be equal to the thermal energy and 66.9 joules. So why is that? Because this region is kinetic energy transferred for thermal energy. And for the first part, so for the first part, what we have is we have the spring potential energy all transferred to your kinetic energy. So this part is your kinetic energy all transferred to thermal energy. So the first part is thermal energy transferred to kinetic energy. The first part is the spring potential energy transfer to kinetic energy. The second part is kinetic energy transfer to thermal energy. So here, this is 1/2. Spring potential energy is 1/2 kx squared, and then equals to 66.9 joule. And then you can get your x will be equal to square root 2 times 66.9 divided by K. And then it's 2 times 66.9 divided by 640, and you are going to get 0.457 meter. So this whole process is the conservation of energy, okay? Spring energy transfer to kinetic energy transfer to thermal energy. So this is that, and let's take a look at 89. So 89, take a look at 89. Okay. So a 2.5 kilogram beverage can is thrown directly upward from a height of 4 meters with an initial speed of 3 meters per second. The air jack can be negligible. So what is the kinetic energy of the can as it reaches the ground at the end of its fall? You have to use conservation of energy, okay? And B, when it was halfway to the ground. So this is A, this is B, and What are the kinetic energy of the can and the gravitational potential energy of the can? Earth system 2.2 seconds before the can reaches the ground. So it's here, 2.2 seconds. So we have to do our calculation. So how to do that? You can, for part A and part B, it's very easy. You can use kinetic energy plus potential energy. So initial, I'm going to write this. Yeah, let's do this. Ka plus UA will be equal to KB plus UB. Okay, so all the parts kinetic energy are conserved. So in the initially, we have 1/2 m 3 square, initial 3, right? Plus mg h, I'm going to do v initial square, so you know. H initial will be equal to, when it's A is 1/2 m VA square plus A is on the ground, so it's 0, and then plus, and it will be equal to all the parts energy conservation. Plus mghb. Okay, so when you do your calculation, you can get your Ka. So say Ka, K is the whole thing here. Your Ka, which is this little guy here, your Ka will be, so do this part, your Ka will be equal to 109.25 joules. And then I also want my Va, because we have to calculate the last part. So it's 9.35 meters per second. And then our Kb, this HB here, this is 2 meters. You put everything in, your Kb should be equal to 60.25 joules. Okay. V initial, let me write it here, 3 meters. H initial is 4, and H A is 0, HB is 2. Okay. So after that, you can put everything in, you can do your calculation. This is a very simple calculation. And for the last part, you have to calculate what is the displacement here, so that you can calculate your kinetic energy. So you can use the kinematic equation, which we had in our class, is y will be equal to y final t minus 1/2 gt squared. Okay, so our T final, when it reaches the ground, is 9.35. So you can get y will be equal to 9.35 times 0.2, and then minus 1/2, 9.8 times 0.2 squared. So you do the calculation, you are going to find out this little distance here is 1.67 meter. Okay, so after you find out this, and you can also find the velocity at there. So the velocity at this point, you can use conservation of energy. Actually, okay. So you are going to calculate the kinetic energy and the potential energy. So potential energy is this. U will be equal to mgy. So use 1.67 is 2.5 times 9.8 times 1.67. You are going to get 40.9 joule. Okay, and also your kinetic energy. Actually, you can use the total mechanical energy here. So it's E minus 40.9 joule, and you are going to get 68.3 joule. Okay, so you can use the total kinetic energy you got here, and then you can have the kinetic energy at this point. So its conservation of energy happened through the whole process. So this is the answer. And we have another problem. 106. 106. 106 is very simple. Okay, so we can do that. The spring in the muzzle of a tri-spring gun has a spring constant, which is 700 newtons per meter. To shoot a ball from the gun, first the spring is compressed, then the ball is placed on it. Think about spring and then ball and then shoot. Okay. So what we are going to have is the ball leaves the spring just as it leaves the outer end of the muzzle, and then the gun is inclined 30 degrees to horizontal. A 50-gram ball is shot to a maximum height. So this is the maximum height. Be very careful, okay? From the gun's muzzle, and assume L jack on the ball is negligible. So what speed does the spring launch the ball? So I'm going to calculate V initial here. And assuming the friction on the ball within the gun can be neglected, what is the initial compression distance? So we should have K 1/2 mv squared. And this is due to the spring. So do this. So at the initial launch, so here, this point, initial, we are going to have K initial will be equal to 1/2 mv initial square, and the U initial will be equal to 0. And okay, and at the top, we are going to have K final will be equal to 1/2 mv initial square, and then U final will be equal to mgh. And these two, they equal to each other, right? These two. And what we have here, we are going to have 1/2 mv initial square will be equal to, so this plus this will be equal to this plus this. 1/2 m, and our V initial, it's V initial x is V initial times cosine 30 degree. Put like this, plus mgh. And from here, you will be able to get your V initial. So V initial will be equal to, so this is cosine 30, is square root of 2gh over 1 minus cosine 30 squared. And then you will be able to get 11.98 meters per second. So this is the initial launch speed from conservation of energy. And this launching speed is all coming from spring potential. So the gun, so here. So this K initial is coming from the spring potential energy. So you are going to write it like this. Oh, this is a little confusing because your spring, oh yeah. Yeah, you may be able to get yeah, because there is also some potential energy. Mm. How do we can we just do 1/2 mv initial square equals to 1/2 k compression delta x squared, and then 1/2 times 0.0, 1/2 times 0.057 kilogram multiplied by our initial speed, which is 11.98 squared will be equal to 1/2 7,000 times delta x. So if I do this, what I will get? Square. So it's 0.057 multiplied by divided by 700. Yeah, okay. So you are going to get 0.11 meter. Okay. Yeah, use this. This is much easier than doing other things because the D is very small. So yeah, use this. You are going to get the potential energy from the spring all goes to the kinetic energy of the ball. Okay, so we can use that. And the last problem. Yeah, I need to end class here for today. For the last problem, I'm going to write a solution and then put it on D2L. Okay, so I will put the solution of this guy 29 and also the solution of 122 on D2L later. And our recitation, I want to stop our recitation today because it has already been an hour and a half too long. Okay, so here I'm going to stop here for today. We have two more problems that we didn't finish. I'm going to put it on D2L later. But tomorrow we are going to continue chapter 9 and we are going to have an exam on Thursday. Okay, so bye.